Hello everyone, this is Dr. Webb. In the last video we introduced vectors. So vectors, remember these are, think about them as lines with arrows on it. So these are objects that have a magnitude, a length, and they go in a certain direction. So we call this one V, and if we want to write the components of it, so if this V goes x naught to the right, y naught up, we'd write this vector like so. X naught kind of y naught. Remember, we use the angle brackets to differentiate this from a point. So what we're going to be looking at in this video is starting to do some algebra with vectors. So in particular, talking about what addition is with vectors and something called scalar multiplication. So let's start off with adding vectors. So let's start off with two vectors. So here's my V. Here is a vector W. And what we mean when we say adding a vector is we mean sort of putting the vectors end to end and see where you add up. So it's kind of like you go along vector V and then you go along vector W. Where do you add up? What does this give you? And so since vectors, remember, these are not dependent on location. And so if I copy these, so they have the same length and the same magnitude, they're the same vectors. And so there's my V, there's my W again. And so if I do this together, while I started off at this point here, and then if I go along V and then go along W, I ended up at this point here. And so that allows me to draw a new vector that goes from the starting point of V to the end point of W, and this is what we're going to call V plus W. And so that's what vector addition is. So what is this going to mean to the components? So let's say we have two vectors, U plus V. So let's there's our U. There's a V. So let's say that U has components A comma B. And so that means that U takes you to the right A, up B, and then V has components C comma D. So you go to the right C, go up D, and so then the question is, what then would be the components of the sum of the two? So starting at U, going along U, then attaching V to the end up here. That's our vector U plus V. Well, if we're looking at the components of this, how far in total to the right did we go? Well, we went to the right A when we did U, and then when we did V, we went C more. So the X component of this is going to be A plus C. And then what about the Y component? Well, when we did U, we went up B. And then when we did V, we went up D more. So the total amount we went up was B plus D. Okay, so the upshot of this is that if you want to add two vectors together, the addition, to get the components of that, you add the components individually. So add components of U and V to get U plus V. Okay. So based on this, let's talk about some vector addition rules. So the first one is it doesn't matter what order you do the two vectors. So this is, commonly how we think about addition anyways, with regular numbers, and it follows the same when we're adding vectors together. But this rule for vectors actually has a special name. So if we have that being u and that being v, but then on the other hand we did v first and then u. So this is v, this is u. Well, since the top and the bottom are the same vector and the left and the right are the same vector, same vector means that they're parallel to each other. So we made a quadrilateral. We're ending up at the same point because addition is the same. This quadrilateral has opposite sides parallel to each other, and so this makes a very natural parallelogram. Where the sides are u and v, and so we call this the parallelogram generated by u and v. And then what then is the sum? Well, the sum is that diagonal right there of the parallelogram. U plus v is one diagonal of the parallelogram. And so sometimes you can think about this, that the addition doesn't matter. This is saying either way you do the addition, you're getting the same diagonal of the parallelogram. And so some people think about this and they call this the parallelogram rule. For the next rule, so this is what's called associativity. And so this is if you have three vectors. So if we have u and then v and then some w, well, when we add these together, it doesn't matter whether or not you do u plus v first and then do w, you end up at that point there. So this is going to be the sum of the three of them. So doing u plus v, then plus w gives you the same thing as doing u plus v plus w. And so it doesn't matter which order we add them. No matter what, the sum of the three of them is the same. Okay, so we talked about addition. What then does subtraction mean? So let's say we want w to equal u minus v. Okay. Well, if we want w to equal u minus v, that's the same way as saying that if I did v plus w, I should end up with u. Okay, so let's draw these out and let's think about where w fits into this picture. So let's say there's u. Let's have v start at the same place. There's v. Now I want w to be set up such that if I do v and then w, v and then w in some way, I end up at the end of u. So after doing v, if I start at the origin and then I do v, I end up here, and then I want to end up at u. So to get to u, I'm going to have to connect that together right there. And so that's what my w is going to be. That's the vector that's such that when I do v and then w, I end up with u. Okay? And so if we, sort of like we did before with the addition rules, if I make the parallelogram here, what is this w? Well, this w, which is u minus v, is the other goes along the other diagonal. And so when you write this other diagonal and you want to know which way should the arrow point, well, the arrow should point to the end of the positive part in the subtraction. Okay, so now we can do addition and we can do subtraction. Okay, so let's talk about what's called scalar multiplication. So we now can add vectors together. And so if I have a vector v, well, one vector I can add it back to is I can add it to itself and get a new vector that's v plus v. But that's sort of, not the easiest, not the way that we're most used to saying it. So what should v plus v be? Well, really, it's two v's. Right? And then if I add another v to that, well, and I'll draw the sum up here, that should be three v's. Right? In the same way, if I start off with v and I cut it in half, so I make it so I have two of the same vector adds up to be equal to v. Well, what does it make sense to call this vector? Well, it should be 1/2 of v, since two of them add up to be v. And so from right here, we get this notion of what's called scalar multiplication. So far I've been doing this with whole numbers and rational numbers, but you can really do this with any any positive real number. And so given some vector v, if we let L be greater than 0, then LV is the vector in the same direction as V, but L times as long. And so, since the addition is done component by component, well, what's happening with this multiplication here? Well, this multiplication is also going to correspond component by component. Let me show you what I mean. So if we did 2 times the vector 3, let's do this in R3. We haven't been doing that yet today. 2 times the vector 3, 1 minus 2. Well, so that would mean adding 3, 1 minus 2 to itself. But then if we're adding it to itself, that really is saying add the vectors. Which means really we just took this 2 and multiplied it to each of the components. Right, so that 2 there gets distributed to each of the other ones. Right, so what does this mean? Oh, come on. There's a bigger eraser. so in general, L times A comma B comma C, let's do this in R3. R2, it's the same idea. It's going to equal LA, LB, LC. What if L is negative? Well, what's the negative going to do? Well, if L is negative, we can do the same distributing L to the inside. So same distribution to the components. And what's that going to end up doing? That's going to flip the vector in the opposite direction. So it flips the vector in the opposite direction. All right, so let's see. You're not working. Okay, so let's clear out a little bit more space here. So what I mean by this, but negative numbers flip it in the opposite direction. So if we have V is 1, 4, then negative V, so that's just multiplying both the components by negative 1, is going to be minus 1 minus 4. Okay. And so if that's V, then minus V, I said it's not a good V. It's more like 4, 1 than 1, 4. Let's make this somewhat more accurate V. Okay, so 1, 4 should look more like over 1 up 4, so that's more like a 1, 4. And so what's minus V going to do? Well, it's going to go to the left 1 and down 4. And those almost look like negatives of each other. Right? And you can kind of tell if you do 1, if you do V and then went back down minus V, you'd end up back where you started. And so V plus its negative adds up to going nowhere, and so that's the 0 vector. Okay, so scalar multiplication rules. So remember, for R2 or R3, the idea with scalar multiplication is L times ABC is equal to LA, LB, LC. So we call this scalar multiplication. This L here is what's called a scalar. Why does it make sense to call it a scalar? Well, what's L doing? Well, it's not really changing the direction other than flipping it into the opposite direction if it's negative. So if it's positive, it's keeping it the same direction, but it is stretching how long it is. Okay. And so the scalar multiplication rules are, so I just wrote the two main ones right here, is if I scale a vector u by k first, and then scale that by L, that's the same thing as scaling it by L times k together. And so this one is really just saying that L times k times, say, a vector AB in R2 is going to equal L times k A L times KB. And then also, since addition is done component-wise, and it plays well with multiplication, it follows a distributive rule. That means that we have this distributive rule in general. So if I do k times u plus v, that's the same thing as k times u plus k times v. Okay, and so this is sort of a distributive. It's not just sort of a distributive rule. It is exactly a distributive rule. Let me put in one other rule here. So how does L affect the length of U? So this is, remember, the bars, the absolute value bars on the other side is asking about the magnitude of U. So this is asking about the magnitude of L times U. Well, so if U is AB, we do L times it. This is going to be L times A squared times L plus L times B squared, which is going to be L squared A squared plus L squared B squared. And so I can factor an L squared out. Times A squared plus B squared. And then I can pull, since it's squared inside the square root, I can pull it out and end up with an absolute value of L times A squared plus B squared. And this A squared plus B squared, that's the magnitude of U. So if I do the magnitude of L times U, this is equal to absolute value of L times the length of U. Okay, so a lot of this nomenclature and ideas for vectors really came about to describe forces in physics. And so this is really a real natural application. And sort of the underlying idea of especially mechanics is that forces can be represented as vectors, and that forces act together. If you have multiple forces acting on something, they act on them additively, right? So if we have some particle in space and it has one force pulling it that way, and it has another force pulling it that way, what's the total force on it? Well, what we're going to do is we're going to add the two vectors together. So there's another copy of F2. And so then the total force is going to equal F1 plus F2. And that's what's going to be causing the motion, or affecting the motion of the particle. And so then another foundational rule, goes back to Newton, is that if a particle or an object is at rest, in fact, it's not just at rest, really it's just has no acceleration, so it could be moving, but just not accelerating anywhere, then the total force on it is 0. Okay? Or another way to think about this is the forces cancel themselves out. Okay, and so when you took, say you have some particle, one force is pulling it this way. Well, if it's not moving, there must be some other force there canceling that out. So, if you think about the way to think about this is we know that on Earth, we can think about ourselves being on rest, but we also know that gravity is pulling us down. So if we're not moving and gravity, the force of gravity is pulling us down, what must be happening? Well, the ground underneath us must be pushing us back up at the exact same force. Okay, so let's run through an example like this, sort of focusing on this force cancellation. Okay, so in this example, we have a weight is held in place of at the origin of the XY plane by two taut ropes. The first rope is at the point runs from -3,4 to the origin, and the second runs from 12,5 to the origin. We can assume that these ropes are straight lines. If gravity is pulling straight down along the y-axis with a force of 100 newtons, what is the tension of each rope? So tension just means how hard is the force in each rope that's pulling to keep it in place. Okay, so let's draw a quick picture. So our weight here is at the origin. Okay, gravity is pulling straight down, and we said that the total force of this is 100. So if we want it to be 100 straight down, what are the components of this going to be? Well, it's not pulling left or right at all, so it's going to be 0 in the x component and then 100 in the y component. Okay. And then we have two other ropes. So one going to 12,5. And so we'll call this T1. And this is pointing out to the point 12,5. The other one is going to -3,4. Let's call this T2. Okay. And so since the weight is being held in place, it's not moving at all, that means that we must have the total force on the object must be 0. And so that 0 is the total force, and that has to equal the sum of gravity plus the tension in the first weight, in the first rope, plus tension in the second rope. Okay. And so the goal here is to figure out we know what G is. We're trying to figure out what are these forces. Okay. So we know that ropes, the force has to be pulling along that length, right? And so the force T1 has to be pulling in the same direction as 12,5, but we don't know exactly how hard it's pulling, but it has to be in the same direction. So T1 has to be some scalar multiple of 12,5, because it has to be a force going in the same direction as a vector from 0 to 12,5. Similarly, T2 has to be in the same direction as the vector 3,4, -3,4, and so it's going to have to look like a scalar multiple of -3,4. Okay, so let's put this together. Double check. That before? Nope. Should be minus. So we had, let's use back. 0 is equal to G, which was 0, 100. plus 1 is L times 12.5 plus T2 is K times minus 3.4. And so 0 vector is just 0, 0 is equal to 0, 100 plus 12L, 5L plus minus 3K, 4K. Okay, so we can focus in on this component by component. The 0, 0 on the left-hand side isn't going to do much. And so if we look at the x component, well, we have 0 is going to be equal to, on the right-hand side, we have 12L minus 3K. For the y component, we're going to have 0 is equal to 100 plus 5L plus 4K. So we can move that 100 to the other side. So we have minus 100. Actually, this should be minus the whole time because it's pulling straight down today, because we're going down. So the y component is minus 100. So we move it to the other side, that's going to turn into plus 100. 5L plus 4K. Well, see, now when we broke this up component by component, now we have two equations, two unknowns. We can use any way to solve this we want. So for me solving this, I'm going to focus in on the x component first. From the x component, I can take this equation, rewrite it as 3k is equal to 12L, divide by 3. I get k is equal to 4 times L. Okay, and so then I can plug that in to the other equation. And so then I have 100 is equal to 5L plus 4 times K. Well, I know K is 4L. So I have 5L plus 16L, which in total is 21L. And so what is L? Is going to be 100 over 21. K then is 400 times that. It's 4 times that, so that's going to be 400 over 21. Okay. So then that means that T1 is 100 over 21 times 12. So that would be 1200 over 21, comma 500 over 21. And so the force is going to be the magnitude. And so that's going to be square root of 1200 squared over 21 squared plus 500 squared over 21 squared. Let me pull out a calculator. It's a little bit too big to do in my head. So I want to do square root of 1200 squared plus 500 squared. And then the whole thing is divided by 21. And so this is 61.9 newtons. And so then what's the magnitude of T2? Well, T2, let's clear out some space here. So T2 is k times minus 3, 4. So T2 is going to be minus 1200 over 21, comma 4 times that is going to be 1600 over 21. And so then the magnitude of T2 is going to be, plug this into the calculator, 1200 squared plus 1600 squared, whole thing divided by 21. And so this is going to be about 95.2 newtons. Okay. And so if you notice, these two, the two tensions by themselves, they add up to more than the 100 newtons that gravity was pulling down. So what's this extra, more than 57 newtons going to? Well, it's going to the fact that T1 and T2 are pulling against each other to the left and right. And we can actually tell that we did this right by the fact that the amount that T2 is pulling to the left is equal to the amount that T1 is pulling on the right. So we add those together, those two are canceling themselves out, but they're still feeling the tension in the rope, in each of the ropes from pulling that. And so because these two are sort of fairly far apart, they actually have to pull against each other because the angle between them is fairly wide. They have to pull against each other fairly toughly, a fair amount, in order to get the, in order to hold the weight in place. Okay, that is all I have for you right now, and I will see you later.